Hello, welcome to the Tech Talk. I'm Min-hyuk, a software engineer working at Samsung Research. In this talk, I'd like to introduce the research achievement of my team related to a well-known distributed framework, Apache Spark. In our research, we have designed new solutions to resolve memory problems in Spark for robust data processing. Today's talk will be present in 4 sections. First, I'd like to talk about my team, who we are, and what we are doing in our research. Then, I'm going to tell you an overview about Apache Spark, its core concepts and architecture. After that, I will present our research lineage-checkpoint approach. At the last section, I'd like to tell you the future research roadmap of my team. First, let me introduce my team. My team is TerraScale Learning and Analytics Research Group called Tesla. We have done a lot of researches about data processing frameworks, which are essential for large-scale data analytics. These frameworks are capable of running in distributed environments for exploiting computing resources for action processing. Especially, we focus on finding out limitations of open-source frameworks such as Apache Spark, PyTorch, TensorFlow, and Apache Druid. And we are designing solutions to overcome their limitations. In doing so, we are aiming at more large-scale and high-dimensional analytics with better performance. And we've maintained our research outputs as Samsung inner source, and our ultimate goal is to release them to public as open source. We've also made several contributions to open source data framework projects. Before introducing our research, I'd like to show you a brief overview about what is Apache Spark. Apache Spark is a distributed framework for large-scale data processing. It's an open source which has been widely adopted in many big companies and startups for their services in production. It has been around longer than a decade, being actively maintained by a large community of developers. Along the way, a well-established ecosystem has been built and expanded, centered around Apache Spark with various software stacks. Spark has been well known in its in-memory speed processing with its efficient data management using memory. According to the official benchmark test, Spark is up to 100 times faster than MemReduce, one of traditional distributed frameworks. In terms of usability, people can easily develop data processing pipelines and services on Spark with high-level APIs and a rich set of functionalities it provides. Specifically, it provides various packages like Spark SQL, Spark ML, Spark Streaming, and GraphX, which enable users to build up their own applications from query processing, machine learning, stream processing, to graph processing. On top of that, it can be easily integrated into different environments, being compatible with Hadoop, Kubernetes, various databases, and so on. For these reasons, Apache Spark has become a de facto in large-scale data processing. I'd like to introduce one of the core concepts in Spark, RDD, which stands for Resilient Distributed Dataset. This logical concept indicates an immutable dataset which is partitioned and distributed across multiple computing nodes, as shown in the figure right side. Data processing on Spark is applying a series of transformations on RDD. In other words, in a Spark application, a user can define a series of transformations from an input RDD to an output RDD using Spark APIs. Each series of transformations is called Spark job. Running a job, Spark applies each transformation one by one on RDD until it produces the output. However, since the data in one RDD can be huge, Spark divides it into partitions and computes them in parallel for better performance and scalability. For running an application, Spark forms a cluster which consists of 2 types of components, one driver and multiple executors. A driver is coordinator for job scheduling in a Spark application. To be specific, driver splits one big job into small steps called stage according to its optimization strategies for efficient processing. Considering the dependencies among stages, it plans tasks, the physical execution units for a stage, and assigns them to an executors. Once all tasks for a stage have been finished, then the driver schedules tasks for a next stage, and so on all the way till it finishes the entire job. On the other hand, an executor is a JVM process where actual task executions take place. Once a task is assigned to an executor, it applies a setup transformation to an RDD partition using the resources on the computing node. Sometimes executors exchange data one another if they need the RDD partitions located in other executors as their inputs. This exchange of data between executors is called shuffle. For a successful execution, each of these components should maintain necessary information. For example, a driver maintains an entire history of RDD transformations, job progress, and locations of RDD partitions. The driver utilizes this information in job scheduling, task assignment, or recomputation on a job failure. Executors maintain cache data, which is repeatedly used in multiple tasks. They also temporarily maintain intermediate output partitions being produced by running tests until they finish. Till now, I briefly explained what is Apache Spark and how it works. For more detailed information, please refer to its official website. From now on, I'd like to explain about our research. This research is related to a memory problem in driver. This memory problem is caused by an excessive amount of objects accumulated in driver. We first tried to solve this problem with an existing way around, but we found that it brought another inefficiencies. So we come up with a new solution we called lineage-checkpoint. As I already explained, Spark driver maintains a history of RDD transformation from an input to an output RDD. This transformation history is called data lineage and is usually represented as a directed acyclic graph DAG of RDDs. Driver schedules tasks for each RDD according to the dependencies in its data lineage. While Spark runs an application, this information is maintained till the end for fault tolerance. Because if Spark loses some of RDD partitions due to an executor failure, then it needs to know the data lineage of the lost RDD for recomputation. For this reason, driver always maintains data lineages during the execution at all time. However, these data lineages can grow huge as RDD transformation keeps being applied. This often happens especially in iterative executions such as machine learning applications. Since in such applications, a number of transformations are repeatedly applied to an RDD over many iterations. This makes the data lineage longer and longer, so it may cause severe memory pressures in driver. As an example, as shown in the figure on the right side, we conducted an experiment with PageRank, one of well-known iterative applications. And we observed that the data lineage grew drastically over iterations. At a certain point, it starts taking up a significant amount of driver memory and causing excessive garbage collections. On top of that, we also observed that the long data lineage introduced overhead in job scheduling. Since driver needs more time to scan the dependencies of RDDs in such long data lineage. And at 400th iteration, driver eventually end up in a process failure due to out-of-memory error caused by an excessively long data lineage. This long lineage problem I described has been around for a long time. To deal with this problem, most of Spark users currently use data checkpoint. With data checkpoint, a user can store an intermediate output RDD into a file system and cut off the data lineage lying before the checkpoint as depicted in the figure. This solution reduces the length of a data lineage and so relieves memory pressure. However, it brings another inefficiency such as disk I/O and data serialization. Such codes can significantly degrade the performance when the data to be checkpoint is large. Figure at the bottom shows well the amount of the inefficiencies caused by data checkpoint. In this experiment, we perform a data checkpoint at 260th iteration. Though it may release memory pressures, we observe that it introduces a massive amount of overhead for saving data in disk at the iteration. Moreover, we also found out that it sometimes breaks data locality information, and the broken locality induces another heavier overhead in the following iterations. According to the things we observed in this experiment, we conclude that data checkpoint is not a good way to solve this problem, and we need a better solution. So we designed a new solution named lineage-checkpoint. The core concept is simple. Instead of checkpointing the entire data, we checkpoint only the data lineage. In other words, we first cache an RDD and then set aside its data lineage. When the RDD needs to be recomputed due to an executor failure, then we can just restore the data lineage and recompute the missing pieces. According to the result in our experiment, this solution effectively resolved the memory pressures and performance degradations caused by long data lineages as shown in the figure. Note that global data checkpoint is checkpointing RDD partition on a global disk like HDFS to keep them safe from executor failures. Unlike global data checkpoint, local data checkpoint uses the cache layer on executors to checkpoint RDD partitions with the sacrifice of fault tolerance. As shown in the figure, our solution effectively removes long lineage problem and shows the best performance with almost no additional overhead. Additionally, compared to local data checkpoint, lineage checkpoint is more fault tolerance as shown in the figure at the bottom. In this experiment, we checkpoint data with each solution every iteration and make executor 1 failed at iteration 3. In this setting, when executor 1 failed, local data checkpoint couldn't recover because it has already removed the data lineage and also lost the checkpointed data on cache layer, so it was unable to recompute the missing data. On the other hand, at the executor failure, our solution brought back the data lineage and successfully restored the missing data. In conclusion, lineage checkpoint approach efficiently resolved the long lineage problem without any additional overhead or a sacrifice of fault tolerance. We have published this achievement as a research paper to Big Data Conference last year. For more detailed information about our research, please refer to the full text of our paper. For the last, let me talk about the future research roadmap of my team. Now, we keep working to improve data analytics frameworks to be more performant and reliable. In doing so, we have published research papers. Meanwhile, we are exploring for more in-house applications where we can try our research outputs. For this, we'll make a release for internal distribution first, and we plan to make open source contributions too. Additionally, we are building up an in-house data warehouse solution, and we are considering Apache Druid as the query engine for the solution. We hope to find something to improve Apache Druid along the way. We hope this talk helped you to understand what is Apache Spark and the related research we did. Thank you for watching.